Carbon-2 nitrogen-14 represents the extreme edge of chemical stability, where molecular bonds are so strained that the slightest touch triggers total structural collapse. Known formally as 1-diazidocarbamycyl 5-azidotetrazole, this compound features a unique arrangement of high-energy nitrogen chains surrounding a central five-membered ring. With an atomic ratio of nearly 90% nitrogen, this molecule contains almost no carbon backbone to stabilize the energetic nitrogen-nitrogen bonds. The primary cause of its explosivity is the massive energy release when nitrogen atoms break their weak single bonds to form stable dinitrogen triple bonds. The compound possesses a high positive enthalpy of formation, exceeding 800 kilojoules per mole, meaning it stores immense energy within its own bonds. Friction and impact sensitivity tests show that even moving the crystals or touching them with a glass rod results in an immediate supersonic detonation. Sensitivity extends to the electromagnetic spectrum, where exposure to low-intensity ultraviolet light or even standard X-ray radiation initiates a runaway reaction. Attempts to characterize the molecule using Raman spectroscopy failed because the low-power laser beam provided enough energy to detonate the sample instantly. The central tetrazole ring consists of 4 nitrogen atoms and 1 carbon atom, forming a heterocyclic structure with high ring strain and electron density. 3 separate azide groups, consisting of 3 nitrogen atoms each, are attached to the ring, creating multiple sites for rapid gaseous decomposition and expansion.
Long chains of nitrogen atoms are inherently unstable due to the lone pair repulsions between adjacent atoms, which significantly weakens the covalent bonding framework. During detonation, a small volume of solid rapidly transforms into 7 moles of dinitrogen gas, creating a massive increase in entropy and pressure. The detonation velocity of this compound is estimated to be over 9,000 meters per second, placing it among the fastest chemical explosives known. First synthesized by the research group of Thomas Klapoetke at the University of Munich, the compound pushed the boundaries of high-energy density materials. Chemists must handle this material in milligram quantities, often using specialized blast shields and remote manipulators to prevent fatal laboratory accidents and injuries. X-ray crystallography reveals highly distorted bond lengths and angles within the azide groups, indicating that the molecule is locked in a metastable state. Unlike some stable explosives that require a primary detonator, this molecule undergoes self-ignition when subjected to even minor changes in ambient pressure. When compared to trinitrotoluene, this azide compound is several orders of magnitude more sensitive, making it useless for military or industrial applications. The thermal decomposition begins at exceptionally low temperatures, meaning the molecule cannot be stored safely at room temperature for extended periods without degrading. Even in solution, the compound remains dangerous, as the evaporation of the solvent can leave behind dry microcrystals that detonate from their own weight. The high concentration of lone pair electrons on the nitrogen atoms creates a repulsive electronic environment that further destabilizes the already weak nitrogen bonds. Every decomposition event of the nitrogen chains is highly exothermic, releasing heat that immediately triggers the decomposition of all neighboring molecules in the sample. This molecule represents the practical limit of chemical energy storage, where any further increase in nitrogen content would prevent the molecule from existing. The solid-to-gas expansion ratio is so extreme that the resulting pressure wave can shatter nearby laboratory equipment and metal containment vessels effortlessly. While thermodynamically favored to explode, the molecule only exists because of a very low kinetic energy barrier that is easily overcome by external stimuli. The energy of a nitrogen-nitrogen single bond is only 160 kilojoules per mole, compared to 945 for the triple bond. The peak detonation pressure reaches several gigapascals, which is sufficient to instantly pulverize carbon-based materials and disrupt metallic crystal structures and targets. Specific vibrational modes of the azide chains can be excited by acoustic energy, leading to resonant bond breaking and subsequent full-scale molecular detonation. Creating such a long, contiguous sequence of nitrogen-nitrogen bonds is a landmark achievement in synthetic chemistry, demonstrating the limits of high nitrogen catenation.
On the standard impact sensitivity scale, this compound records a value below 0.25 joules, meaning the smallest falling weight triggers it.
Even a tiny static discharge from a human finger or synthetic clothing provides enough electrical energy to overcome the activation barrier of this sensitive azide. The lack of efficient orbital overlap between the azide groups and the tetrazole ring prevents the delocalization of charge, which would otherwise stabilize the molecule. The primary decomposition products are purely dinitrogen gas and small amounts of solid carbon soot, leaving behind almost no other chemical traces after detonation. Supercomputers struggle to model the transition states of this molecule because the potential energy surface is incredibly complex and filled with steep descent paths. Recent research into these energetics often occurs at the nanogram scale, where individual molecular interactions can be observed without the risk of destroying laboratory equipment. While too sensitive for use, this molecule serves as a model for developing high nitrogen propellants that release only dinitrogen gas, making them environmentally friendly. The molecule is often discussed alongside octaazocubane, which is a hypothetical cube of 8 nitrogen atoms that would be even more energetic and unstable. The internal angles of the tetrazole ring are forced into positions that deviate from their natural bond preferences, creating immense internal tension within the ring. The 3 nitrogen atoms in an azide group typically form a straight line, but in this molecule, they are warped by the proximity of other groups. It is classified as a primary explosive of extreme sensitivity, requiring special plastic containers that dissipate static charge and prevent any physical shock during transport.
The breakage of a single bond releases enough thermal and kinetic energy to overcome the activation energy of every other bond in the molecular structure. Its energy density per gram is significantly higher than conventional explosives like RDX or HMX due to the absence of heavy oxygen or chlorine atoms. As a primary explosive, it transitions from burning to detonation almost instantaneously, a property known as the deflagration to detonation transition, which occurs in nanoseconds. Synthesis must be performed under an atmosphere of ultra-pure argon gas to prevent any reaction with moisture or oxygen in the air, which could catalyze decomposition. When excited by light, the molecule undergoes a rapid electronic transition that shifts the electron density into anti-bonding orbitals, causing the atoms to fly apart. Researchers use diamond anvil cells to compress the molecule to millions of atmospheres to study how it might become stable under extreme planetary core pressures. The lack of toxic byproducts makes high nitrogen compounds the holy grail of energetic research, despite the extreme dangers involved in their initial discovery and testing. The activation energy required to trigger decomposition is so low that thermal fluctuations at room temperature are sometimes enough to provide the necessary energy. Study of this molecule paves the way for new classes of materials that could provide more efficient propulsion for long-duration space exploration missions beyond Earth.
Ultimately, carbon-2 nitrogen-14 defines the boundary of what is chemically possible, challenging our understanding of how many atoms can be held together. With its 14 nitrogen atoms in a state of constant energetic tension, this compound remains the most sensitive and explosive chemical ever created in a laboratory.